Hi there and welcome to my Lab 2 screencast. So we're starting Lab 2 by using the same markdown file that we used in Lab 1, which is your donkeys one. You can download it from Stream if you have misplaced it. And we're just going to start by just running everything that we did last time. So we're going to run all chunks above. Okay, just so that we're got all the data in and all up to date. And we're going to start by visualizing the model. So we're going to be using VisReg for this. So we're going to be loading the VisReg library. Okay, if you don't have it, you can install it via the packages menu. Just click install, type in VisReg, and off you go. And then once we've loaded VisReg, we're going to visualize the model LM1, which is the first model that we did last time, the plain straight line model that we did last time. And we can see here that the model fits okay in the middle, but is underestimating the data at either end, right? So right, a curve is probably more appropriate. So let's try visualizing the second model that we did last time. So we also did another one, I called it LM2. Okay, and when we do this, we see that the x-axis is on the normal scale, right, standard heart girth, but the y-axis has the log of body weight rather than the body weight, right, and it's curved. And the relationship is curved, and as you can see, it is actually fitting the data reasonably well, but of course the log body weight isn't a particularly useful sort of thing to set up. So let's try a transformation. So when we do the VisReg, we'll add in a transformation. So we'll add in the opposite to log, which is the exponential function. And we'll also add partial equals true. And the reason we do that is if you don't, so this is the transformed thing, right? That's transformed the body weights back to the usual scale, and we've got our fit, but we don't have any longer where the points are, and that's what the partial equals true adds in. Okay, so there's the representation of each point and the fit, and you can see that it's fitting the data much better now. Also note that the y-axis label is kind of a little bit goofy, so we could fix that with ylab. Sorry. Anyway, in kilos inside the VisReg. There we go. Okay, so this model seems way better as it's passing through the average body weight. Much better, particularly at the ends. The confidence bands are larger at the ends, in particular at the high end here, because we have more freedom there, right, to tilt the curve up or down due to less data. No, don't even need that really. Yep. Okay. So now exercise 2, we're looking at the multiple regression. So we're going to start by extending our previous model. We're going to create a new one, LM3, which is going to have body weight in terms of heart girth and umbilical girth. So this is similar to what we did in the what we covered in the lecture. Okay, let's look at this model summary. Okay, so we notice the coefficient of heart girth has changed. It was 2.83 in LM1. This is because the variables are correlated. As heart girth changes the input. And you can see that if you take these two coefficients and add them together, you get about the same order of magnitude as we had before. So the p-value for girth is 2 times 10 to the power of -8, i.e. tiny, is testing whether umbilical girth tells us anything about the body weight after accounting for heart girth. So our conclusion here is that body weight depends on both heart girth and umbilical girth. Both are useful, and we've explained about 82% of the variation in body weight by using both girths. Okay, now we're going to add length and height as well. So we'll take our one from before and call it something else, LM4, and add in length and height. Okay, now we get obviously another row each for each of those, and we see that that height is not important. P is 0.065 for explaining body weight if we've after accounting for the others. Right, so height basically doesn't give us anything extra, but this isn't to say that height is not important. Obviously it will be. Right, taller donkeys are likely heavier, and of course, you know, if we just did a regression with just the one, what are we up to now, 5? Right, just with height, then obviously height's going to be important, right? Right, so clearly height's important. The p-value is really tiny. In fact, height explains 61% of the variation just by itself. So height's definitely useful. It's just that if you have the others, it's better to use the others. The others are more useful than height, if you like. Okay. So So now we'll take the one we had before and we'll drop height out because it's not useful, but we'll add in sex just to see what happens. So I think we're up to number 6 now. So we're going to take height out and replace it with sex. And you remember that from lecture 2 that when we, to put sex in as a variable, we include an indicator variable, right? And so R will set up those indicator variables for us automatically. And so we get a coefficient for male. And interestingly enough, you find that sex is important, right? It has a low p-value. So sex is included in the model using an indicator variable. So female will go into the intercept and we'll get a difference between female and male donkeys. So males are on average 2.9 kilos heavier than females, all else being equal, a same size, so heart girth, umbilical girth, and length, but one is female and the other male. Male will likely be heavier by 2.9 kilos. Okay, so there's probably something else that's not measured purely by size that accounts for the difference between male and female donkeys. So perhaps it might be muscle mass or differences in anatomy or something that explain the different sizes, right? To slightly different shapes, perhaps. Okay. And so that's interesting because when we had sex by itself in lecture 2, right, we saw that sex wasn't important, right? So we've got two different scenarios here. We have, this one here where height was important by itself, but when we included other things, height was no longer important. And then when we looked at sex, where we look at sex by itself, it's not important, right? See lab 2 for that, lecture 2 for that. But when we look at sex after adjusting for size, it is important. And the reason is that once we've adjusted for size, we've adjusted for essentially a lot of the variation within each group, right? So in order to detect a difference in sex, you've got to be able to detect the magnitude of the difference between the female and male groups in terms of the average shifting, accounting for the variation within each group, right? And the variation within each group, if we don't have any of the numeric measures, is really big, and so you can't see the small difference in the average between each group. But once you've explained a lot of the variation within each group, because small donkeys are small, small donkeys are light, large donkeys are heavy, after we explain all that, we essentially reduce the amount of variation within the female group and within the male group, the leftover variation, and now we can see the magnitude of the difference between the groups. Okay, so that's what's going on. Okay, let's look at visualizing this model. So we could use VisReg for that. So what are we, LM6? Yep. Okay. So when we look at VisReg, we've got 4 plots, one for each variable. So there's the heart girth one, the umbilical girth, the length, and then the sex. The residuals in these ones are now what's called partial residuals, in that they're not true representations of the data. So for example, in this plot here with the sex, you can see that the biggest thing we've got is, it's calling a body weight of about 100 and maybe 165 kilos. But whereas in fact we know that the biggest donkey is about 200 kilos. So these are representations of where the donkeys are in terms of their weight after adjusting for the other variables, right? So essentially what we do is we take the effect of heart girth out. We take the effect of umbilical girth and height and length out, and what we've got left over is then sort of what's represented on the plots, all right? So that's the difference there. Okay. So you'll notice that the length relationship isn't really as strong as the heart girth one, right? It's got much more spread around it. Same with the sex. There's way more spread around the trend line there, around the average, which makes sense, right? You can't explain anything really if you've just got difference between sex. So anything that's been explained here has been explained really by the other covariates. And what was our overall? Okay, so our overall R squared was now up to 85%. So we're explaining much more in the model. The last thing we'd want to do is probably check the diagnostics. And I suspect we'll find that there's an issue here. Okay, let's have a look. Yeah, so we've got, oh, maybe it's not too bad. We've got some slight curvature. We've got mostly positive residuals here, but there's only a few of them really. You know, once you eliminate kind of 3 or 4 of them, it's actually pretty good. So it's not as bad as it was, but we still are getting that fanning of residuals, so probably the linearity and equivariance assumption aren't ideal. Normality seems okay, no real problems, and there doesn't look as though we have any influential points. There's nothing past these Cook's distance lines here, so we should be okay there. So perhaps we could investigate a transformation. It's a little bit tricky. Probably what I'd try just transforming the outcome variable maybe. So just transforming the body weight. I'm not sure if I would transform the others. Possibly transform the other numeric measures, but obviously you can't transform the grouping variable because it's just a group. So we might be able to try that and see if that makes any difference. That's something that perhaps you might want to play with a little bit. So I'll just finish by writing something a little bit about that. So linearity and equivariance aren't ideal. Maybe we'll just try that real quick, eh? See what happens. Worth a go. So we're up to 7, I think. So we're going to let's take that original LM6. And we'll try and log. So first we'll just try the outcome variable and see what happens. And really at this point we're just interested in the diagnostics. So I'm just going to look at the have a look at the. Okay, that's maybe okay. There's a slight curve there, but I think it's mostly driven by really the couple of points at each end, really. Let's take the smoother off, see whether we. Yeah, so without the smoother there, I mean, maybe it's not ideal, but let's have a look at the summary. Okay, we're explaining a little bit more variation. Everything's still important, as you would expect. The numbers are kind of a little bit odd now because, of course, everything's on a log scale. Let's just try logging the other numeric variables as well. See how this goes. See whether that helps at all. Okay, that's actually pretty good. That looks nice now, actually. Let's have a look at our summary. Okay, everything's still important. We're now explaining almost 87% of variation. So we could maybe look at visualizing it with VisReg. Probably I should have these in different. Let's put these in different chunks so you can see. see them later. So we'll want to transform the outcome variable back. So let's do that. We have to change the Y label. Okay, so yeah, so these are looking a bit better. So there's only really a slight curve really in the heart girth. Interestingly, a curve the other way around in the umbilical girth, although essentially that could be straight, right? So we possibly, and the same with the length. So it's not actually all that strong as far as the curvature goes. So it's just really a slight improvement. Obviously, the problem with making it, this sort of model here is that it's more complicated now to use for prediction, right? You can't just, it's not just, with the original model, we could just write down what the equation was and we'd be done, basically, right? And so, for any computation, you just pop the heart girth, the umbilical girth, and the length into the equation. It's just a bunch of multiplication and addition, and you get your answer. Whereas now we've got to log them first and then exponentiate the outcome, so it's a little bit more cumbersome. And again, really, the original model probably would have been completely fine, through the bulk of the data, right? So if you're only interested in sort of, donkeys in the usual range that donkeys are in, then you're going to actually be okay. It's only if you're worried about the small ones and the big ones that you'll want to be sticking with the log model. I expect that if you actually exponentiate this, then it's probably something like, it's heart girth to the power of something times umbilical girth to the power of something times length to the power of something times a different coefficient depending on sex. So that's what the actual formula would be. So it's a power curve relationship like we saw before. I think I wrote a little bit about that in the solution to lab 1. All right, I'm going to stop now, and we'll have another video for exercise 3, the petrels one.